Hi, my name is Zachary Williams, and today I'll be doing a presentation for you on tuberculosis. So the main topics that I want to discuss with this are going to be the origin and the discovery of the bacteria causing the disease, which is the Mycobacterium tuberculosis bacteria. I want to look at its taxonomy and the structure of the bacteria and kind of some of the factors that might aid in its own survival. I want to look at the pathogenesis, how it spread, as well as our body's innate and adaptive immune responses towards it. The epidemiology, kind of discussing a bit about where it's prevalent and some of the different factors as to why. Our treatment options to deal with it, as well as some preventative measures in dealing with it in the future. So the origin of tuberculosis is kind of an interesting one because it's supposedly been around now for a very long period of time. It's hypothesized by some scientists that there's been this disease around since even up to 20,000 years ago in East Africa. And unfortunately, at that point, there wasn't exactly written records to be able to prove that for us or not. But some of the earliest documents that we have been able to uncover from as early as 2000 BC show that there are characteristic similarities between tuberculosis and a disease that was seen back then. Another interesting fact is that tuberculosis does have the potential of being able to cause deformities. The main one being kyphosis, or like a hunchback type appearance, which is seen even in some mummies from that time period. Now, of course, it's a disease that's definitely prevalent even to this day, but it has plagued human society for generations and generations. It's been across the Roman Empire, it's been across the Greeks, it's been seen at the Middle Ages and the Renaissance, and again, we still experience it today in pretty great numbers. So Mycobacterium tuberculosis was a little bit difficult to discover. It did take a little bit of time because we needed to have a better understanding of exactly what microorganisms are. So it wasn't until the 17 and 1800s until any real great progress was made. At the time, the disease was known as consumption or phthisis, and the earliest discussions and written things about it were mentioning how at the time they believed that in some way coming into contact with a microorganism was most likely its cause. So of course, over the next 100+ years, scientists went and conducted many different experiments and recorded a lot of data trying to compare diseases and try to see what was what. And we, of course, were able to kind of determine a lot of the different characteristic features that come about with this disease. Everything from breathing issues, coughing, fever, abscesses forming, fibrosis, necrosis, pleural fluid buildup. They were also later able to discover that it didn't just affect the respiratory tract, which was the main thing, considering that it enters initially into the lungs and kind of grows in the alveoli. But we discovered later, of course, it can be in the bones, it can be in your gastrointestinal tract, it could be in your nervous system as well as your lymph nodes for your lymphatic system. So in the late 1800s, Robert Koch is the man who was able to discover the root cause of tuberculosis. He found the Mycobacterium tuberculosis and was able to isolate and grow that tubercle bacilli, that is the shape that it is, which earned him a Nobel Prize in the early 1900s. As far as the taxonomy goes, Mycobacterium tuberculosis fits into a group that's oftentimes called the Mycobacterium tuberculosis complex, or the MTBC. It does have other variants that are in there as well, but this because it's other animal species that are also able to be affected by it, such as the Bovis or Africanum versions as well. Mycobacteria are known to being a slow-growing, non-motile, and chemo-organotrophic organism. They don't produce spores, though they do still grow very similarly to fungi, and they are an aerobic bacillus. So the full taxonomy of it has it in the domain Bacteria with the phylum Actinobacteria. Within that phylum, there's 6 different classes, and one of those classes is also the Actinobacteria as well. So that's why it kind of shows up for both phylum and class. And then under that, you're going to have the order, which is the Actinomycetes. You have the Mycobacteriaceae for the family, Mycobacterium genus, and then Mycobacterium tuberculosis for its species. And the structure is pretty unique when it comes to tuberculosis because the the start is going to have a complex cell envelope to kind of help protect it, being mostly made up of polysaccharides and proteins. Within this, you're going to have your plasma membrane, which helps to retain its integrity and gives it support. But one of the most interesting features is the peptidoglycan, the arabinogalactocan complex, or AGP. And this is what's kind of helping make up the core of the cell wall. It has cross-linked polymers of the peptidoglycan, giving the arabinogalactan polysaccharide branches that are going to have mycolic acids towards the ends. And this has got some goods and bads for us because these branches are helpful. We're able to use that portion of the bacteria as a biomarker for identifying its existence within our bodies, but also the mycolic acids that are present there do form a pseudomembrane that has a hydrophobic effect that does help deal against our own antibodies and other host defenses we have against it. So we're going to have the pathogenesis here, and primarily when it comes to TB, it comes from you inhaling it in some way. And when you inhale it, it's able to sit within your lungs in the alveoli, the little air sacs that are present there, where it can replicate. And the time frame does vary. It could be 2 weeks, it could be 8 weeks, it just kind of depends. And so, of course, our bodies aren't going to be able to get any type of direct response against that until it grows enough to start being more prevalent and our body can recognize it. Of course, against it, we're trying to use macrophages and dendritic cells primarily. And so they're going to be mostly housed within the alveoli just because the initial infection is primarily housed in the respiratory system, within that alveoli where it originates. And so we're trying to prioritize having as many macrophages there as possible to kind of help destroy it as needed. So the main thing we're going to be looking here is the different PAMPs, which there are several different ones, but we have the lipoarabinomannan, we have the phosphatidylinositol, and the heat shock proteins HSP65 and HSP70. These are going to be what helps us to notice the disease, but we also have some nucleic acids that are present that can be used for this as well, primarily picked up by our toll-like receptors, being toll-like receptor 2, 4, and 9, like CpG motif. So the recognition by these different toll-like receptors is primarily there to help get those cytokines moving so we can get that inflammatory response started. But it also is going to help us with initiating phagocytosis to consume and destroy the pathogen with phagosome-lysosome fusion and acidification. For the adaptive response, it's a little bit different because it needs to be prevalent in our body for a period of time so that we can have a more dedicated response against it, not just an initial response. And dendritic cells are also going to be very important here too because they're going to help trigger that phagocytosis, but they're also going to help start moving some of that infected cells towards our T cells, which are going to have additional support for us too. So once the antigens can be recognized in our lymph nodes, we can start having CD4 T cells activate, and then they're going to start moving to the lungs, further preventing the mycobacterial growth. The main thing with the CD4 T cells is that they produce interferon gamma, which is trying to activate macrophages. It also stimulates that phagosome maturation and induces apoptosis in those infected cells. It's also going to help out with activating the ROS, which is reactive oxygen species, which are commonly going to be produced or enhanced during bacterial infections, and they're going to help out with trying to work with that inflammatory response, but also with self-signaling to kind of get things in motion. Of course, one of the big considerations we have to note here is that CD4 cells are going to have issues in people that are immunocompromised, so we'll look more about that here in just a minute. With the epidemiology of the disease, it's important to note that it is still found everywhere, but it is primarily located in regions of Africa and Asia. It's suspected that it began in Africa to begin with, specifically East Africa, and it still seems very prevalent in these particular regions today. But there's a lot of different reasons that might cause for heightened levels of the infection to be in these different regions. And the first is going to be HIV co-infection. We've seen already that with HIV disorders, the immune system is compromised. And as a result of this, we're going to have that lower number of CD4 cells that are necessary in helping us to combat the disease to begin with, which just makes it harder for us to fight it. It's going to require longer duration treatment to be able to deal with. Some of the interesting situations might be in the case of prison environments, but also with migrant populations, because a lot of people can carry this disease in a latent form and don't actually know they have it. The latent form of the disease has it present in your body, but it's not active and it's not causing you any symptoms and it's not causing spread. But when conditions are met that make your immune system weaker and allow you to start having those symptoms, now you can start spreading it to other people. So in prison environments where nutrition is probably not the best, medical facilities are not exactly up to par as they would be in some other areas, and you're so tightly packed together with other people, it's easy for it to spread, like with any other sickness that you'd find in a prison. Migrant populations as well could be moving to different countries and not know that they have the issue to begin with. They could be originally from a region that has a higher prevalence of the disease, move somewhere else, and then depending upon their conditions then, the latent infection can turn to an active variant and they can start spreading it. Drug resistance is also going to be a big deal because there's strings of antibiotics that are necessary in order to treat this, but depending upon compliance with them and how easily a person is going to be identified for having tuberculosis, many different factors can affect whether the drugs are going to actually be effective or not. And over time, resistance can build up, especially if they're not used properly. Various different social determinants are mostly referring to things in your environment that might cause for you to have a weakening of the immune system, whether you have other illnesses or it being poor nutrition or overpopulation in a particular area. There's many different reasons as to why your environment can kind of activate this against you. So the latent TB infection is that kind of hidden variant, and you can be discovered to have latent infection before it actually causes issues for you or you spread it. And if we can identify that, that does help out in treatment processes for sure. COVID-19 does play a role. There's been different time periods in history where tuberculosis has become more or less prevalent. Early 2000s, 2012, I believe, and of course, right around when the COVID epidemic began. But in the case of COVID, it's kind of unique because with COVID, it was such a priority to understand and know who had COVID and who didn't. Our diagnostic ability against TB actually decreased somewhat. And so the focus on COVID-19 actually took away our focus at being able to identify and quickly treat tuberculosis, and it did cause for a little bit of a rise right there early on in the pandemic as well. As far as the treatment options go, like I said, there's a string of antibiotics that are used for this all at the same time. The main four are the rifampin, the isoniazid, the ethambutol, and the pyrazinamide. These main four are the usual starting treatment antibiotics that are given to patients, and the duration for this varies from several different factors, but the general duration is 6 to 9 months. Sometimes you might go for a shorter, more intensive variant of this that might be 4 to 7 months. And then, of course, if it's the case of a latent infection where you're trying to remove it before you start dealing with the symptoms and being able to spread it, it could be as short as 3 to 4 months. But in the case of you having this and you're dealing with the resistant version of it where it's already fairly resistant to these antibiotics, maybe you weren't compliant with how you were taking them, or maybe you just have a really strong strain, there's also additional medications that can be provided after the initial treatment options have been provided. So fluoroquinolones, injectable antibiotics, amikacin are just a few examples of this. And depending upon how bad the infection is and kind of what they're able to tell from testing, this could last 2 to 3 years in some cases. So the duration of the treatments can end up being quite large. And then we're mostly going to be looking here then with prevention of tuberculosis, because that's kind of one of the best ways to help prevent it. We already have at least in 2022, between 8 and 9 million cases in a single year. So doing what we can to kind of prevent tuberculosis is also incredibly helpful as well. Early detection is one of the biggest things. Being able to treat TB before it actually is in an active state and before it gets out of hand is key. This is going to make it a little bit easier for medications to be able to defeat this particular bacteria. But also, we want to make sure people are very compliant with how they're taking their medications. I know a lot of people don't necessarily listen to the doctor's orders on how they should take their medications. So taking things for the prescribed amount of time when you're supposed to each day is incredibly helpful to prevent you having any relapses of that infection or it becoming more drug resistant, which is going to then extend the duration of your treatment. Of course, for individuals that are known to have or have been around individuals with TB, it's really important to have patient screening. Patient screening is a great preventative option for being able to find people that may have the latent version of the infection, which is a little bit easier and less time consuming and also costly to prevent. But it also just gives us a little bit of a leg up in trying to prevent more and more cases from coming up more quickly. As well, there are certain conditions that are kind of ideal. Of course, being with a good nutrition plan, having things that can help strengthen your immune system, taking your vitamins, obviously trying to prevent being sick is great. Being vaccinated and having good respiratory hygiene are helpful. Even just good ventilation and UV light are also helpful factors when it comes to just trying to prevent that spread and contraction of tuberculosis. But of course, we also have to think about who we're around and trying to make sure that we're in conditions where we can hopefully not get sick in general. And this would be my list of references. I hope you guys enjoy. Thank you so much.